Okay, so we are recording. Good. Okay, so this is lecture 2. I know that if I start, you'll show. That was the. Yeah, we guessed there's a range, so yeah. Right. Very good. So we are going to discuss this Hamilton's principle of extraction. So this was around 1800s. The thesis that Hamilton produced geometric optics, and then this was a byproduct. Its application to mechanics was noticed by himself and by other people. His main thing was optics stuff. So I'll tell you. Okay, so let's recall this, what we did last time. We had this Lagrangian. Basically, Lagrangian approach to mechanics. So you start with the Lagrangian. In general, is a function of Q dot E. And then we have this action functional. So S of Q, which is integral T1 to T2, L of Q dot E. And this Hamilton's principle says that the path of motion, mechanical motion, so this is the Hamilton. Although, of course, as we discussed, it has long history in the work of Euler, Lagrange, Fermat, all these guys. But Hamilton kind of consolidated everything. So that motion ut is along, motion is along paths, critical paths. Critical. So what does this mean? So there is one equation which we just wrote as delta of S equal to 0. That's too brief, or but what it really means, it means that immediately we should, even anytime you see this equation, you should have the following in mind, that this means that ddt of S of Q plus S epsilon at S equal to 0 is equal to 0. This is for all epsilon from T1, T2 to configuration space Rn such that epsilon of T1 is equal to epsilon T2. Now notice we are saying for all epsilon. So what does this mean? It means that, yes, this is the path, from A to B, the particle actually takes with respect to given this action. But this path is such that any perturbation, like by epsilon of this, so this would be Q plus epsilon S. And then as you change S, you get closer and closer supposedly to the path. So this is really directional derivative of this functional in the sense of calculus along the direction epsilon. So we are saying that what is the critical point? The critical point is a point where all directional derivatives vanish at that point. That's okay. So yeah, so that's a definition. Is a good one, but we have to find out how to use it. So the lemma is the following: Qt is a critical path if and only if it satisfies the Euler-Lagrange equation. It satisfies the Euler-Lagrange equation. They may be equations. So I write first one equation. So this would be ddt of dl dq dot minus dl dq equal to 0. Okay. So here, of course, we are thinking of L as a function of independent variables Q, Q dot, and T. And this is partial derivative with respect to second variable. And then you sub in Q, and it has to satisfy this equation. Obviously, this is a second order ODE, second order differential equation that has to satisfy. And of course, if you are in Rn, you can put Qi here for all coordinates, basically. I mean, Q is equal to Qi. I found one. So there are system of n second order ODEs. So proof of this is not difficult. So what we have to use, we use Taylor's theorem. So apply Taylor's theorem to this function L of Q dot T. And then what we know is that we can write something like this: L of Q plus S epsilon, and then Q dot plus S epsilon dot, and T is equal to, so is equal to the value of the function at the origin for S equal to 0, and then there is a first order derivative contributions, and second order is going to be squaring it. So it's going to be equal to L of Q dot T plus S times here dl. I mean, so if we take derivative of this with respect to the first coordinate, dl dq, and then there is this S, which is the derivative of this guy with respect to S. And plus dl, so here S epsilon dot dl dq dot. And then, okay, so I'm afraid I'm off here. And then plus okay, I can write here plus dl dt times dt ds. But t is independent of s, so this term vanishes completely. And then plus terms which are of second order in s, or s squared. So now, when we try to make sense out of that derivative. So now this derivative ds of s of q plus epsilon, sorry, s epsilon. Yes, okay, good. At s equal to 0, this is equal to 1 over limit as s goes to 0 of 1 over s integral from t1 to t2. And then we have to put in corresponding Lagrangians and subtract, right? Because s is integral of Lagrangian. So this is L of, we just put the value here, q plus s epsilon q dot plus s epsilon dot t minus L of, and then I've got q dot t, and then so this term of order s squared, when you divide by s, there is still a term of order s, and you take the limit, this doesn't make any contribution. Right? So, and because of this, so you see that this integral is equal to the integral limit. So this is basically equal. And this s, by the way, cancels with that s, and this s over here. So what remains is basically integral t1 to t2, right? S dl dq of, well, dl dq, just that. I'm afraid I forgot to put epsilon here. So I'm taking them, so there should be dl dq, and then limit of this with respect to s. There's a little problem here. So q plus s epsilon, q dot plus s epsilon, and t. So this is the original one. I have my notes. So do you know why I'm on a puzzle at this stage? Which is why you want that thing. I also need s. Yeah. Because I'm dividing by s. Right. So and here is
Why don't they have?
Sorry?
Why don't they have it? It seems like.
Yeah, so I have to take the derivative of this guy.
Yeah.
With respect to S, because I'm expanding around S now. S is the value. So I'm taking the derivative of this guy with respect to S. So because this with respect to X, there's only epsilon dot remains.
Are you taking the derivative with respect to S down there or up at the, like in the new line?
Of this one, of this function. I'm expanding this, right? Because it appears here.
Yeah, but are you expanding it in Q and Q dot?
Yeah, but all of them are now functions of S.
Yeah, yeah.
So this is a function of S, so I have to take the derivative with respect to the first variable, which is Q, and then I have to put the derivative of this with respect to S, which is gives me an epsilon, and the derivative of this Q dot times the derivative of this with respect to S, again is Q dot, and then this doesn't contribute, and I subtract this term disappear, and then I've got this term without S. But I want to divide by S.
But they do have S. The up one is S epsilon, S epsilon dot. It has the S one.
No, but I just put it wrongly. I'm thinking.
Oh, no. When you Taylor expand the first order terms, you Taylor expand with respect to S. Come on the term S, right?
Yes. They should be there. Yeah, so sorry. This is correct, but I was confused somehow.
Yeah, there's a lot of variables there.
Yeah. It's always like this in driving.
Yeah.
So yeah. Okay. So anyhow, right. So this becomes dl dq. Yes. Times epsilon plus dl dq dot. And then I've got times epsilon dot, right? dt. So this is the variational derivative, so to speak. Now, what we are assuming, we want to have this equal to 0, right? So then I just put this equal to 0. Now, here's the punchline. Here is epsilon dot. We have to get rid of epsilon dot. And the whole thing is to use integration by part. So once you use integration by part, and you use the condition that epsilon t1 equal to epsilon t2 equal to 0, you can write this in the following form. It's equal to integral t1 t2 dl dq minus ddt of dl dq dot times epsilon times dt equal to 0 for all perturbations. You see, I changed epsilon dot by using integration by part into this term using this type. Okay. So now, what is the condition for a critical path? So the condition is that Q must satisfy this equation for every epsilon. Now, of course, if you have a function, for example, continuous, such that its integral multiplied by any function is equal to 0, that function, original function, has to be 0. There's no way for this to be non-zero and to have this for every epsilon. And the reason is that the moment that you have something non-zero, like this, you can cook up an epsilon which vanishes at these 2 points and exactly picks up values which are non-zero at those points. And for those epsilons, this integral is not 0 because it has a positive contribution. So this is used to be called fundamental theorem of calculus of variations, but it's a very easy fact of analysis. So from here we get that dq minus ddt. And this is the famous Euler-Lagrange. Okay. So are there any questions?
The Hamilton's principle is a sort of first order condition. Are there any generalizations of it? You get other equations?
Yes, there are generalizations. You go to second order. So there is this second order functional derivatives, which is more complicated, and there is also this functional determinant, is more complicated, and that tells you if the function you have got is it a minimum or maximum. So there is a story of multivariable calculus repeats itself, but in this infinite dimensional functional derivatives, functional calculus frame.
And are they must be useful or something?
They are useful, yeah. They are useful in some places. But for us, for now, we are just not getting into that.
Yeah, of course. Just curious.
Yeah, sure. So we won't discuss that. This is the Euler-Lagrange. So Lagrange derived this using other principles of mechanics, not this minimization principle. Yeah, so we use D'Alembert's principle, which is a different foundation for mechanics. It's a bit different from this, but it was Hamilton really who, I will tell you what was Hamilton's concern. Okay, so any questions so far? Yeah, we are not going to be concerned with finer analytic details which are not of importance for us. Okay, so now let's look at a couple of examples. Please. So this would be example 1. So then let's look at the classical Lagrangian, which is L of Q dot T equal to kinetic minus potential. Equal energy, so this is equal to, say, m over 2 q dot squared minus, and then potential energy is something like du. So we are assuming that the particle is in a force field, which is conservative, as we discussed in the last lecture, and is given by that, but we want to write a Lagrangian. We don't know about Newton's equation so much. We just want to write some Lagrangian. And this Lagrangian is the standard Lagrange, kinetic energy minus potential. And so what is the Euler-Lagrange equation in this case? Well, in this case, obviously, the LDQ is equal to negative. I mean, yeah, this is nonsense. I should put U, sorry. Yeah, potential. Right, so the LDQ now is, because this is a function of Q after all, right? So it's equal to the UDQ. And there's a negative sign there. Okay. And the L dq dot obviously is equal to m q dot. So with the Lagrange equations, so what is that? That's just gives us that indeed ddt of m q dot minus du dq equal to 0. But this is m q double dot minus du dq equal to 0. And this is ma equal to m. So this is nothing but Newton's equations for a conservative vector. Newton's equation that we met in the last lecture. So Lagrangian mechanics contains Newtonian mechanics as a very special case. But the point of Lagrangian mechanics is that it can be applied in contexts that Newtonian mechanics cannot say much. But Newtonian mechanics has its own features also that maybe Lagrangian mechanics is not capable of absorbing. I mean, so there are some aspects of Newtonian mechanics quite powerful. I think how to put it. Okay, so I'm guessing, so let's not get into that. I mean, so I don't want to stick with any question? Yeah. From the Lagrangian. Right. That's absolutely possible. And by the way, for this reason, the LDQ is called generalized force. It has a name. It's called generalized force. That's one thing. And this DL, I mean this DL dq dot. I mean, so where is it? Yes, DL dq dot. This is called generalized momentum. Yeah. So we call it generalized momentum. So if you think about it, then basically Lagrange's equation, or the Lagrange equation, it just says that the derivative of generalized momentum is equal to generalized force. And this is, of course, again, Newton's equations, if you think about it like that. So it's a generalized Newton's equations in a way. Because Newton's equation, you can also think about it. Because A is like ddt of ma dot equal to F. But this is momentum, right? But this is nv. A dot is q dot, sorry, is velocity, and this is m times velocity, as we'll see, is called momentum. So, yeah, it looks very different at first. This Euler-Lagrange equation looks very different at first, but it's really a generalized form of Newton's equations at the end. Question?
It'd be a dumb question, but can you ever have kinetic like contribution that doesn't look like this?
Yeah, it depends on coordinates, but so the art. So yeah, we have to give some more examples. But the art of yeah, I'm actually the example I'm going to give. It doesn't look like this. Oh, okay. So now I hope it is really this form. But yeah, I think it is. So let me give you the second example. Yeah, I think that this was a good question. Okay, so let's now look at example 2 then. This was actually the original motivation for Hamilton, example 2. Geometric optics. So, what is the problem of geometric optics? The thing is the following. You have a medium, like air, for example, here, which is not homogeneous. So we have a inhomogeneous, but it's isotropic medium. And we want to study the path of light in this medium. So there is one quantity in this case that characterizes the medium, and that's index of refraction. So n of x, y, z, which is by definition is equal to speed of light divided by the velocity of light. The velocity of light in the medium. This is speed of light in vacuum. This is speed of light in the medium. So this is called the refraction index of light in a inhomogeneous isotropic medium. So inhomogeneous means that this n, of course, varies from point to point, but isotropic means that really for the light, it doesn't matter in which direction it's going. In all directions, it has the same speed. You can imagine that there be some complicated medium that speed of light also would depend on the direction. In that case, it would be like a tensor. It's not going to be just a scalar function. So that would be more complicated. That's why we have tensors, because you have these quantities that depends on the direction of the things. But here we are just to simplify, we are going to assume this. So, any question? Yeah. So now the question is can you give me an example of this thing this question, the situation that happens in reality from day-to-day experience, where index of refraction changes from point to point?
Change in mediums, right?
Yeah.
Like going from to a glass of water.
That's one case, yeah. But so in that case would be like a piecewise linear or piecewise constant, so to speak, function. But something even perhaps more interesting, maybe.
Maybe the medium's density changes.
Yeah, exactly. The medium's density changes. For example, the air, when air is in areas that's hot, it has less density, so the light goes faster. And when it's cold, it's dense, more dense, and light goes slower. So you can imagine that this n really changes from point to point. So this could be a very practical problem, actually. And I'll give an example that it actually is something that you have experienced, I bet. Okay, but for now, so the problem is this. So the light goes from A to B. So the problem is find the equation. Find the equation of light ray. Of course, so we are talking about the light ray in this medium, right? So, and the answer to this question is based on Fermat's principle of least time, as we discussed last lecture. So Fermat's principle of least time. So this t, which is integral, I don't know, from A to B, I just write it like this. So what is time? Time is equal to, so velocity, if you want, is equal to the distance taken divided by time, right? So then time is equal to, distance divided by velocity. So S divided by Now the velocity is equal to c over n. So this becomes 1 over becomes 1 over c times cs. Okay, so this is the kind of calculation. You should do it for yourself when you're thinking about these things. But then this gives us the answer is equal to n of x, y, z. Yes. Well, ds is the arc length, infinitesimal of the arc length. Because what we are doing, we are breaking this into pieces and approximating the time for each small piece. And then we are, and this, so this is basically equal to, there is 1 over c, sorry. This is equal to then 1 over c integral from a to b n of x, y, z square root of dx I can just write how squared plus dy tau squared plus dz d tau. This formula from calculus for the arc. Okay, this is the expression, and this is our Lagrangian. I mean, here is dependence on q dot. I mean, q is really x, y, z in this case. This is just function. So indeed, this is not of the form kinetic energy minus potential energy in an obvious way. And we know that light actually really passes through this through curves that satisfy this, so that minimizes this. So the equation of light is Euler-Lagrange equations. Any questions? Yeah.
There, we've got ds, which is like finding all of d cubed integrated along the path. We've broken up that actually into the decimal Pythagoras.
Yeah, or the interpretation here is that we are breaking up the path into small straight lines, and for each one, the time that it takes is exactly this much, and we are summing over. So this is in the limited approaches to the integral. Riemann sums, of course. So now, of course, solving the equation delta t equal to 0 might be hard, but at least there is one case that it can be solved, and the solution is well known. So let me give you, just to finish this example. Example has to do with formation. There is a phenomenon called mirage. You have seen it. So this is example 3. This is formation on mirage. So what is it? So in a hot day, you are in some desert, or it doesn't have to be even desert. You're driving in a kind of flat road, and you're looking at the highway in front of you, and what happens is that you see the sky in the highway. This gives you the impression that there is water in front of you, and this can happen also on land. people have been trapped in deserts. They have seen water in front of them, but this was just a mirage. It was not reality. It was an illusion. And so, but this illusion exists also in day-to-day, everyday. So basically, you are here, and there is some cloud. And what happens is that you see the image of the cloud. I mean, normally you have in normal day, you see the clouds where they are. But in these special days, the cloud is, you just see it on the ground. So from A to B, we are saying the path of light stuff, instead of being a straight line, is really curved like this. So what's going on? Yeah. Any idea what's going on? Why this happens?
That's because the heat is a change in density, so it warps the path.
Yeah, exactly. And how does it? How does it warps the path, changes the path?
The straight line's the usual path, and it just bends outwards.
Yeah. So indeed, yeah, exactly. So I mean, what happens is that the temperature on the ground is much higher than temperature on elevated parts. And you can imagine that there is a function. So the refraction index depends on, of course, it depends on temperature, which is velocity, but then it depends on the altitude. So here then, so there is no y coordinate. This is just x coordinate, and there is, imagine this is the z coordinate. So n is really like n of z. It's function of height, so elevation. Right? And n here is big, fraction index, and here is so remember what was n? N was equal to c over b. Yeah, it's the opposite. N here is small. As you move up, it's big. So you can imagine n is proportional to h even. Because I'm thinking of velocity. So velocity in thin air is more than velocity in cold air. Okay. So then the light, because it wants to take the shortest time to reach from B to A, it's not good for light to be in cold areas most of the time. It tries to be in warmer areas, so it comes down. But then goes up, because if it just, I don't know, so if it comes down forever like this, you're not getting to A. You're solving the equation connecting B to A. So the solution to this question is known completely. So in this case, Euler-Lagrange equations then, so T is equal to 1 over C integral A to B n of Z square root of 1 plus f prime of x squared dx. You see, this is the arc length, right? Because, I mean, our curve, I just denoted by f of x. This is the unknown curve. And we are connecting x1 to x2. So f of x1 is equal to a, f of x2 is equal to something like that. Right? Okay, this is known. I mean, you can imagine this n would be proportional to z. This could be something like alpha z. This would be proportionality index. And then you have to what am I trying to do? Yes, this is z prime squared. And we want to find the of this equation, this Euler-Lagrange equation. This can be solved. There is something like cosine hyperbolic functions that comes out. You can check it out. There are many sources. Just check out this. And, so this is a cool application of Euler-Lagrange to formation of mirages. There is also the opposite case where near things and near Earth is colder than. That's how you see, for example, ships that are far away. They are below the horizon. You can see their images. Also, when sun goes down, the sun that you see in sunset is actually not the sun at the horizon. It's below the horizon, but you get the image because of mirage. So, and then there is also double mirage, the triple mirage, and all kinds of phenomena. So it's all can be analyzed with geometric objects. So this is some just fun applications, but that's not what we want to do now. So we want to, yeah. So this Lagrange equation is quite nice because it can be done, can be written over general manifolds. That's not it's not a problem. So let me, any question?
That if I plug in opposite or is that integral pretty reasonable to solve right now?
Yes. Yeah, there is I believe some cosine hyperbolic functions. Yeah. And this looks like cosine hyperbolic.
Yeah.
Well, yeah. So it's pretty well known. So, okay. Any questions?
And practicing solve these things and use the numerics, right?
Yeah.
They set it up, they can.
In this case, there is even an exact solution. So this is
Right.
completely solvable. In this case, it's easy. So there is, so this is the Lagrangian. Manifolds. So these manifolds in classical literature, like Lagrange, they call the points on the manifold. They specify points. They call generalized coordinates. So in physics, they talk about generalized coordinates. So this is generalized coordinates. So you see, this Q now is a point on N. So now, so this configuration space, see, you have a manifold M, which is your configuration space. You see, we started with M equal to Rn, right? But it doesn't have to be like that. It can be very general. So any manifold, M equal to Rn is our original configuration space, but it can be. So what is Lagrangian? Lagrangian is a function from the tangent space of M, the tangent bundle of M to R. This is the Lagrangian. I mean, you can even allow yourself some time coordinate, and this is Lagrangian. Now, so what we need above that or beyond that to think about Euler-Lagrange equation. So we want to, we can set up the problem. There's no, I mean, so still the action S of Q, you see, so you look at all paths that connecting A to B on the manifold, and S of Q is equal to integral T1 to T2 L of Q U dot T dt. This quantity makes sense, or is it? It does, because if you have a path Q, you see Q dot at this point is a point in the tangent space. It's a vector in the tangent space. So, and then at the end of the day, this is just the usual integral on the line. It's not a problem. And you want to set up things such that delta is equal to 0. So you can formulate, and then you get Euler-Lagrange equations exactly as we did, same equations. Now with the interpretation that they are true in any coordinate system. So this is the magic of this thing. We have to think about it a little bit. Why these equations are independent of choice of coordinates. I don't want to get into that. Those cases too far in different directions. But that's this can be done. So here's a special example. Mg is a Riemannian manifold. So you have a Riemannian metric on the manifold. And imagine you have a potential U from M to R. Some potential function. And then your thing Q dot E can be the following thing, M over 2 norm of Q dot squared. Because we can't compute the norm now, because norm of any vector, tangent vector, is a square of its length. Riemannian, this is the Riemannian length, minus U. And this is just a generalization of kinetic minus potential. But then now you're over a manifold.
How far can you generalize this? Lorentzian and that?
Yeah, yeah.
Sure.
We can do
About a spectral triple in general.
Yeah, some of it could be.
Maybe that's sort of replaced by this spectral action. What do you know? There's someone done that.
No, I don't think it has been generalized to that context.
Yeah, it's quite exotic context.
Yeah, but it could be useful. Yeah, it could be useful. But so also Newtonian mechanics also can be formulated on Riemannian manifolds. Because I mean, this Newton's thing, it looks like that it's kind of very much tied up to Rn, but you can, at least in one case, you can really write down things. So this is Newtonian mechanics. Manifolds also we can do. So what is the setting in this case? So we just need a vector. So okay. So the setting now is we have just a manifold M. So yeah, let me write it now. So we really need a metric. We don't need a metric. So G. This is the Riemannian manifold. So what? And we need a vector field on it. So F is the vector field on M. Okay. So what is Newton's equations? F equal to ma. What is the analog of Newton's equation?
generalized force.
Yeah, yeah.
Constant here.
We can start with Euler-Lagrange equations.
Yeah.
Yeah, yeah.
Yeah, that's what you're gonna do. I don't know what the end result.
Yeah, so Newton's equations in this case is just covariant derivative of Q dot with respect to Q dot. So this number is covariant. So if f equal to 0, remember we discussed a special case of Newton's equations where in vacuum, for example, there was no force. What was the equation in that case? The acceleration is equal to 0, right? And the solutions were straight lines. And this is exactly acceleration in Riemannian geometry. So in this case, it just tells us that acceleration. You remember what this equation stands for from Riemannian geometry?
A law.
Yes. So we are looking at the past such that the covariant derivative of the tangent vector field with respect to itself is equal to 0. What kind of equation is that? Geodesic, yeah, exactly. That's geodesic. Yeah. For example, over spheres, these are great circles, and over other things. So, yeah, I mean, geodesics are paths of particles on this Riemannian manifolds, which are subject to no force. Yeah, that's right. So we could have, yeah, that's a good point, yes. But in this case, of course, they said you. Right. So yeah, I mean, so this really tied up to geometry. This mechanics is so much tied up to geometry, even from very early stage. Yeah, Q dot. Okay, let's see how much power I have. Oh, okay. So, are we okay for now, or I wanted to say a few words about Hamiltonian mechanics and then move to quantum field theory. Should I say maybe a few words about Hamiltonian? Because this was also discovered by Hamilton, and it's a mystery how it just, okay, I just write down now. So, according to, I think this is going to be the third approach to mechanics, which is Hamiltonian mechanics. We had Newtonian, we had Lagrangian, this is. Yeah.
We're never really interested in setting the issue of the connection. But we were really saying like adding and the connection on just two out there.
Oh, you mean on Lorentzian?
No, I mean like you can define.
Oh, I see. Yeah, yeah, connections. Yeah, I believe
that would be. Is there like a physical application for such a thing?
Oh, I'm pretty sure people have written about that. Yeah. So this is like a, yeah, mechanics in presence of a connection, not a metric. Yeah. But then you can introduce torsion also, It might be interesting to see what is the effect of torsion, what is the physical meaning of torsion.
Torsion.
Yeah, no, I don't write it. Torsion. So Hamiltonian. Okay, so in this case, we start with something called phase space. So this is n. So I mean, in the simplest case, I just start with Rn plus Rn star. So this is the dual space, but you can identify it with Rn. So this is the set of all Q and P. Of course, Q belonging to Rn, and P belongs to Rn star. So we can just, okay, so this is called position and this is called momentum. So phase space consists of pairs of position and momentum. Now, so this is kinematics. Okay. But where the motion is derived from, there is a function called Hamiltonian, which is really the energy function. H goes from Rn plus Rn star to R. So I mean, imagine H goes from the phase space, it's a function of the phase space. The Hamiltonian is just a smooth function of the phase space of the system. Okay, so this is, as I said, is a replacement for the idea of energy in general. And so what are the equations of motion? So we have this like 2 n-dimensional space. And we want to say what has qt dt for particles when it's in this energy subject to this Hamiltonian, how it moves. So these equations were derived by Hamilton. The following, so Hamilton's equations. So it's Q dot equal to dH P, P dot equal to minus dH dQ. Of course, I mean, you have to think that this could be 2 any first order equations, like Qi dot, Pi dot, Pi, Qi dot. There is an important minus sign here. So these are now 2n equations, which are first order. 2n first order. And
But it seems a lot better.
in
some ways. It's at least linear.
Yes, yes. But I mean, are they linear?
Well, okay, the first order, they're not linear, sorry. But
They're not linear because H can be functional.
Yeah.
P squared or P cubed.
It could be better.
In general. But I mean, it has same degrees of freedom, right? Because Euler-Lagrange, we had like n equations, but they were like second order. We have now 2 n equations, but they're first order. So the trade-off is you haven't gained in that regard. Of course, we're not going to get more freedom, less freedom. Same level of that freedom. Or degrees of freedom. But the mystery is how these equations are obtained from Euler-Lagrange. And because Hamilton in the same paper, this was the point, he wanted to reach to these equations. And so it's quite a story, quite a complicated story.
Did he know like the Euler-Lagrange equation?
What's that?
So he had the Euler-Lagrange equation.
He had the Euler-Lagrange
And he
equation.
liked these.
Yeah, and he invented these, and he showed that actually these are equivalent to Euler.
Why did he want these instead?
Okay, so yeah, good question. I'll tell you now why these are much nicer in a way. Okay, not completely. In a way, now. So they have some features. You see some features of motion here that's completely hidden in Euler-Lagrange. Yeah, I will tell you one right away, but then you will see some. You know what I mean? So let's look at some examples. I mean, absolutely the first example. So we have HQP equal to P2 over 2M plus U of Q. So in this case, we have kinetic plus potential energy. This is really total energy now. This is kinetic energy. It's written not in terms of velocity, but in terms of momentum. So it becomes P2 over 2 plus potential. So let's look at now what are the equations of motion in this case. So the equations of motion are very simple because we have got Q dot is equal to what is dHdP? With respect to P, we get P over M. Right? That's really like velocity because P is mv in this case. And P dot is equal to minus dHdQ is minus du dQ. So if you think about it, this is just saying, you just defined, I mean, if you, how to say this? This is also like a tautology. The Q dot is equal to V, and this is like saying that M V dot is equal to minus du dQ. So this is MA equal to Newton's equation. So this, it's a simple thing, right? Because Hamilton's equations in the simple case rewrites Newton's equation, which is a second order for a conservative, which is second order, as two first order equations. And that's something, that's a trick that you know how to do. You have second order ODEs, you could write it as two first order ODEs by calling derivative of y prime as a new value. So for this case, there's no gain really, but we'll see that there is a lot of gain. So this is the simplest case for conservative systems. So what about conservation of energy? So conservation of energy is quite simple to derive in this case. I mean, there's a lemma you can prove that lemma is that energy is conserved. I just write it in a very general thing, but we are talking about this context of Hamiltonian dynamics. So we were saying energy is conserved. So what do we mean by that? Well, it just means that if you take the derivative of H of P QT dt is equal to 0. So basically, you're over your manifold and you're going along some Hamiltonian path. You evaluate energy at each point, you notice that energy is not changing. It's constant. So energy is moving on constant energy surfaces only. That's something we saw also in Hamiltonian, in Newtonian mechanics for conservative systems. So this is the question. Right? We have to prove this. Okay. Proof of this is very simple because what we can do, I mean, we can just write dH, dQ, dQ, dt plus dH, dP partial dP, dt. But on this path, of course, dQ dt is just dH, the Q dot is dH dP. And this is dH dP. I mean, dP, dt, P dot is dH dQ. And this is that's the conservation of energy is just a very simple matter in this case. It's embedded into the. But now notice that so energy constant, they cut down a 2n minus 1 dimensional submanifolds here, generically. But there is one, at least there are many things, but there is one fact which is absolutely mind-boggling and important, and is completely hidden below the surface. And there was no way think this people could see it without this Hamiltonian picture. And that is something called Liouville's theorem. So Liouville's theorem. Liouville's theorem says that not only energy is preserved, in fact, volume in phase space is also preserved. The motion preserves the volume in phase space. Preserves. What does this mean? What does this mean? So you have this space of dimension 2n, right? Rn cross Rn star, for example, which we can think of for now as Rn cross Rn. And so each point, there is a path because of the fundamental theorem of differential equation. Through each point, there's a curve that passes through that point. It's a unique curve that passes through the point. There's no velocity fixing needed because it's first order. So if you put a point, there's a unique path. So you have this thing filled with this path. The phase space is filled with, it's a disjoint union of this. Now, what this result says is that if you take some area here, right, and study its motion, of course it changes, but the volume, total volume, is the same. Volume of this area is equal to 1. So if I denote this flow by phi t, basically what it means is that volume of phi t of any domain D is equal to volume of D for any domain D. This is like a domain. Because you can let the domain move and study this. And this is absolutely mind-boggling result, and it's fundamental result. It's quite important. A lot of things.
So if you have some volume in space and you consider all paths that carry it, and the total volume doesn't change.
I mean, it's like you have the idea that some diffeomorphisms they preserve volume. Like you can have maps from Rn to Rn that preserve volume, and necessary sufficient condition for that, I believe, is that the determinant should be equal to 1. So that's the condition. Here, phi t is a diffeomorphism for each t because it just goes.
Okay, yeah.
Those diffeomorphism is defined by those two differential equations.
Yes.
For Q dot and P dot, you take your points that lie on the
Exactly.
curve to follow.
Exactly. So this is this famous Liouville's theorem, and it's a kind of, at least for us, it's the first time we see that Hamiltonian approach tells us something about motion of particles. It's completely hidden in the function of Newtonian. There's a lot of geometry there. But first, the other picture of Lagrangian has its own features. So you can say Lagrangian is defined over tangent bundle. Hamiltonian is defined over cotangent. So I will motivate that. So for now, maybe we should stop, and then we can just, because my battery is dying anyhow. You're getting tired, I'm getting tired also. So let's